In this video, I will walk you through free response question number 3 from the 2007 EP Calculus exam. Parts A, B, and C pertain to the 5 existence theorems, but Part D is about finding the equation of a tangent line for the inverse of a function. In addition to the first and second fundamental theorem of calculus, there are 5 other theorems that you need to know. The first is the intermediate value theorem, or IVT, which says if f is continuous on the closed interval from a to b, and f at a is less than k, which is less than f at b, there exists some c on ab such that f at c is equal to k. In other words, imagine that f at a is here and f at b is here. Now imagine some value k that is between f at a and f at b. If f is continuous, then we are guaranteed to hit that value k at some point. In other words, we are guaranteed that there is some value c such that f at c is equal to k. And that's the intermediate value theorem. Next, we have the extreme value theorem, or EVT. This is pretty self-explanatory. If f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on a to b. And this is an absolute minimum and an absolute maximum. Next, we have Rolle's theorem. For this theorem, f has to be continuous on the closed interval from a to b and differentiable on the open interval from a to b. And it says if f at a is equal to f at b, then there is a value c in ab such that f prime at c is equal to 0. In other words, imagine that f at a is here, and then f at b has the same exact value. If function f is continuous and differentiable, so there can't be any corners or cusps or discontinuities, then we are guaranteed that there is some point between a and b where f has a horizontal tangent line. We are guaranteed that there is some point c at which f prime at c is equal to 0. Rolle's theorem is really just a special case of the mean value theorem, MVT, which says that if f is continuous over the closed interval from a to b and differentiable over the open interval from a to b, then there exists some c in ab such that f prime at c is equal to f at b minus f at a divided by b minus a. So what does this really mean? The mean value theorem is just saying that there is some point c where the slope of the tangent line is equal to the slope of the secant line. Let's say f at a is here and f at b is here. This purple segment is the secant line. If function f is continuous and differentiable, then we are guaranteed that there is some point c where the slope of the tangent line is equal to the slope of the secant line. Of course, the slope of a tangent line is f prime, and the slope of a secant line is the old school slope y minus y over x minus x. Finally, we have the mean value theorem for integrals, which says that if f is continuous on the closed interval from a to b, then there exists a number c in ab such that f at c is equal to 1 over b minus a times the integral from a to b of f of x dx. Hopefully you recognize this formula as the average value formula. So in other words, the mean value theorem for integrals says that there's always going to be a number c such that f at c is equal to the average value of f of x. So you see that we have 2 different mean value theorems. We have one for derivatives and now one for integrals. But if you ever just see mean value theorem, it automatically means the one for derivatives. if they want to refer to the mean value theorem for integrals, they have to specifically say for integrals. I want to highlight one difference between the two. Notice that the mean value theorem for integrals is about the value of the function at c, just plain old f at c, whereas the mean value theorem for derivatives is about f prime at c, the slope of the tangent line. Let's see how the 5 existence theorems apply to free response question number 3. The functions f and g are differentiable for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f at g of x minus 6. Part A. Explain why there must be a value r for the open interval from 1 to 3 such that h at r is equal to -5. We can use the intermediate value theorem to answer this question, but the intermediate value theorem requires that a function be continuous. So first we have to establish that. Here's a fact I want you to be aware of. If a function is differentiable, it is automatically continuous. So when they tell us that functions f and g are differentiable, we can conclude that they are also continuous. But we must say so as part of our answer. Ultimately, we need to say that h of x is continuous. But if f and g are continuous, then h is also continuous because h is composed of f and g. F and g are differentiable, so f and g are continuous. So h is continuous. We need to state this right at the beginning before we can use the intermediate value theorem. We must explain why there must be a value r on the open interval from 1 to 3 where h at r is equal to -5. Let's line that up with the intermediate value theorem. Let's make a few substitutions. We need to show that there is a value r on the interval from 1 to 3 such that h at r is equal to -5. According to the intermediate value theorem, this will happen if there is a value of h that is less than -5 and a value of h that is greater than -5. So let's see if we can find those. Since we need to find this r that is between 1 and 3, let's find the value of h at 1 and the value of h at 3. Hopefully, it'll turn out that one of these is less than -5 and one of these is greater than -5. Then the intermediate value theorem will apply. In the setup, we are given that h of x equals f at g of x minus 6. That means h at 1 equals f at g at 1 minus 6. Let's work this from the inside out. What is g at 1? Well, here's g and here's 1. So g at 1 is 2. So now we have f at 2 minus 6. But what is f at 2? Well, here's f, here's 2. F at 2 is 9. So now we have 9 minus 6, which is 3. So h at 1 is equal to 3. Similarly, h at 3 is equal to f at g at 3 minus 6. Working from the inside out, we need to find what is g at 3. Well, here is g and here's 3. So g at 3 is 4. So now we have f at 4 minus 6. But what is f at 4? Well, here's f and here's 4. F at 4 is -1. So now we have -1 minus 6, which is equal to -7. So h at 3 is -7. Notice that one of these is less than -5 and one of these is greater than -5. So the intermediate value theorem guarantees that there will be some r where h at r is equal to -5. I was doing my work up next to the chart so you could see the chart as I wrote, but you would really show your work down here. And add, since h at 3 is less than -5, which is less than h at 1, there is an r in the interval from 1 to 3 where h at r is equal to -5. Notice that even though we are using the intermediate value theorem, we don't have to mention the intermediate value theorem. Part B. Explain why there must be a value c in the interval from 1 to 3 where h prime at c is equal to -5. Only 2 of the 5 theorems mention f prime. This one doesn't. Neither does this one. Rolle's theorem mentions f prime, but f prime is equal to 0, not a number. And then there is the mean value theorem. F prime is equal to this expression. In order to use the mean value theorem, the function must be continuous and differentiable. So let's establish that right from the start. I'm going to say the same thing I said at the beginning of Part A, but instead of just concluding that h is continuous, I'm going to conclude that h is continuous and differentiable. We must begin by saying f and g are differentiable, so f and g are continuous, so h is continuous and differentiable. Again, we are making this final conclusion because h is just a composite of f and g. Since h is continuous and differentiable, according to the mean value theorem, h prime at c will equal h at 3 minus h at 1 over 3 minus 1 for some c on the interval from 1 to 3. Remember, h is given by this formula here, so h at 3 will equal f at g at 3 minus 6. G at 3 is 4. So we have this. F at 4 is -1. So that's -1 minus 6, which equals -7. H at 1 equals f at g at 1 minus 6. G at 1 is 2. So now we have this. F at 2 is 9. So we have 9 minus 6, which is 3. So according to the mean value theorem, for some c on the interval from 1 to 3, h prime at c will equal h at 3, which is -7, minus h at 1, which is 3, divided by 3 minus 1. -7 minus 3 is -10. 3 minus 1 is 2. So we get -5. So we have proven that h prime at c will equal -5 for some c on the interval from 1 to 3. Feel free to say according to the mean value theorem, but this is optional. Part C. Let w be the function given by w of x equals the integral of f at t dt from 1 to g of x. Find the value of w prime at 3. The second fundamental theorem of calculus tells us how to take the derivative of an integral defined function. We find the value of f at the upper limit times the derivative of the upper limit minus the value of the function at the lower limit times the derivative of the lower limit. Let's use the second fundamental theorem of calculus to find w prime of x. We need to find f at the upper limit, so that's going to be f at g of x times the derivative of the upper limit, so times g prime of x, minus the value of f at the lower limit times the derivative of the lower limit, but the derivative of 1 is 0, which means that this term is gone. So w prime of x equals f of g of x times g prime of x. So w prime at 3 equals f at g at 3 times g prime at 3. G at 3 is 4. So we have this. G prime at 3 is 2. So we have this. F at 4 is negative 1. So we have negative 1 times 2, which is negative 2. That's it for part C. Part D. If g inverse is the inverse of function g, write an equation for the line tangent to the graph of y equals g inverse of x at x equals 2. Whenever they ask us to find the equation of a tangent line, we love to use point-slope form because all we need is a point and the slope. They gave us the x-coordinate of the point when they told us to find the tangent line at x equals 2. So we know the point will be 2 comma something. The y value will be y equals g inverse at 2. We can use the properties of inverses to help us find g inverse at 2. G inverse at 2 equals y if and only if g at y is equal to 2. Notice that I just switched the x and the y. So g at what is equal to 2? We can find that on the chart. G at 1 is equal to 2. So that means y must equal 1. Now we know that y is 1, and the point of tangency is 2, 1. Next we need to find the slope of g inverse at x equals 2. But in a calculus class, we find the slope by finding the derivative. The slope will be the derivative of g inverse at x equals 2. But finding the derivative of an inverse is a 3-step process. Step 1 is to find g inverse at 2. But we already found that when we found the point. G inverse at 2 is 1. Step 2 is to find the value of g prime at the value that we found in step 1. So g prime at 1. We can use the chart to find that. G prime at 1 is 5. In step 3, we can find the derivative of g inverse at 2 by simply taking the reciprocal of the value from step 2, which is 1/5. So the slope of the tangent line is 1/5. So now we can write the equation of the tangent line. It will be y minus y, so y minus 1, is equal to the slope times x minus x, so x minus 2. Kabam!